time-independent degenerate perturbation theory. First of all, we considered the fact that if an electron is in the 1, 0, 0 state, that is the ground state of the hydrogen atom, it has a certain energy, E0. Okay? And we know that up to first order, if we place this hydrogen atom inside an electric field, the perturbative Hamiltonian becomes minus E0 or electric field and the Z operator, if the electric field is applied along the Z direction, because the application of the electric field breaks the symmetry. So under this perturbative Hamiltonian, we were looking at the changes in energy, the shifts in energy. To first order, there was no shift in the energy of the 1s order. So up to first order, the shift in the energy of the ground state given by HP 1, 0, 0, 1, 0, 0 is just 0. The reason is that this perturbative Hamiltonian is an odd operator. This is a spherical harmonic function, this is spherical harmonic function, both of them are even. So all of this is an odd function, and its integral over all of space is 0. Then we looked at what happened if the electron is in the n equals 2 level. Now we know that corresponding to the n equals 2 level, there are 4 possibilities. There is 2, 0, 0. There is 2, 1, 0. There is 2, 1, 1, and 2, 1, minus 1. So there are 4 possible states. Now the hydrogen atom is at the n equals 2 level, or the single electron inside the hydrogen atom, inside the hydrogenic atom, has been excited to its first exciting state. Okay? And these are 4 degenerate states. And we place this atom inside an electric field. This electron could be an excited hydrogen atom, or it could be a lithium. Lithium would just be 2s in its ground state. So suppose we have a combination of these orbitals. Okay. And what we would like to find out is that all 4 of these orbitals have the same energy. Right? That energy is E0 over n squared, where n is 2, with the negative sign. All 4 of these energies are equal. Okay, so this is a degenerate set of states, different wave functions, but the same energy. Alright, now let's, so all 4 of these states have the same energy, and we would like to place this system inside an electric field that is applied along the Z direction, and we would like to find out what the changes in the energy are. Okay. Now we have to write degenerate perturbation. So what we would like to do, we would like to write the perturbative Hamiltonian HP in matrix form, and we would have to choose a basis, and we would have to choose a particular order. Suppose the ordering that I choose is the following. I use the same order that I did here. So I get terms which are like 2, 0, 0, HP, 2, 0, 0, 2, 0, 0, HP, 2, 1, 0. 2, 1, 0, HP, 2, Alright, so this is the matrix for the perturbative part of the Hamiltonian. Okay. Now each of these HPs is basically this term. It's a Z operator. Now we notice that in the diagonal terms, the L's are the same for the bra and the cat. So this is the same. Now this is an odd operator, the Z operator. Whatever the parity of the spherical harmonic functions, you have the same parity for this function as for this function. So the product of these weights of these functions is even, and you have an odd function here. So all of this goes to 0. Overall, this is an odd function. This is 0, 0, 0, 0. And this crossing out means that this equals 0. Now we have to consider these terms 1, 2, 3, 4, 5, 6. You have to consider only these 6 terms because it's a Hermitian operator. If we know what these 6 remaining terms are, we can, by the Hermitianity property, supply those values in this lower diagonal of lower triangular part of this matrix. Now, if the values of ML are non-equal, then we showed in the previous class that the term vanishes. This term goes to 0. This term would also go to 0. This term would also go to 0. This would also go to 0. And this would also go to 0 because the corresponding ML values in the bra and the cat, they are unequal. So what remains is this term. Okay? So we have to calculate this term. So the problem of finding all the 16 elements inside this matrix is reduced just to finding one element. Okay? And this element would be equal to this element. The complex conjugate of this element would be equal to this element. All other terms will be 0. And if you perform the calculation, if you supply the spherical harmonic functions for the wave functions, this turns out to be minus under root 3 A naught, where A naught is the Bohr radius, with of course a minus E electric field term as well. Okay. So if this is minus under root 3A, this is also minus under root 3A naught. Okay. And all other terms are the same. यहाँ पर माइनस नहीं है, वो माइनस में है. So our perturbative Hamiltonian HP written in a particular basis, in a particular order, is simply given by minus E under root 3 A naught, the electric field, right? E 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. So this is the perturbative Hamiltonian. And the eigenvalues of this Hamiltonian will tell us the first order corrections to the energy of the degenerate states. Now we have to find out the eigenvalues. Now this is not a diagonal matrix. However, we notice that we can immediately break up this matrix into two blocks. This block and this block. You see, if you look at the third row, fourth row, third column, fourth column. In the third row and the fourth column, third row, third column, this is 0. Third row, fourth column, this is 0. Fourth row, third column, 0. Fourth row, fourth column, 0. So there is no non-zero matrix element that connects the third, fourth row with the third, fourth column. Okay. However, there is a matrix element that connects the first row with the second column, which connects there are matrix elements connecting between these states. Non-zero matrix elements connecting between these states. But there are no matrix elements connecting between these states. They are all zero. And none of these states is connected with these states. So this state is not connected with any three of the other states. This state is not connected with any three of the other states. However, these states are mutually connected. So we can break up our matrix into two blocks. Remember that we could have non-zeros here. We could have an A, B, C, D here. Still we could break up the big matrix into small matrices. We just have to find out which of these states that I've written there are connected. Connection means the transition matrix element which sandwiches the two states is non-zero. Okay? So there is no connection between the third and the fourth state with the first and the second, in either the first or the second. So the third and the fourth states form a separate subspace of their own that has nothing to do with the subspace spanned by the first two eigenstates. Correct? So this is how we can break up this matrix into two parts. So the eigenvalues of these states are clear. They are 0 and 0. The eigenstates, the eigenvalues of this block matrix is simple. This is just the poly operator, the sigma x operator. So the eigenstates will be +1 and -1. Right? So and this coefficient carries over, so the eigenstates are -e under 3 a naught capital E and plus small e under 3 a naught capital E. So these are the connections to the energies. But which states correspond to these energies? What is happening here is that we have applied a perturbation and we notice that we get 4 different eigenvalues. In fact, 3 different eigenvalues. Okay? 3 different eigenvalues means the degeneracy has been lifted. Previously, all 4 states that we were considering had the same energy. Now there are 3 possible energies. So the degeneracy has been lifted. The effect of the perturbation is to lift the degeneracy. The states are no longer degenerated. What are the eigenstates corresponding to these states, to these energies? So if I write the eigenstates, so we have placed the n equals to the capital L electron in the L shell in an electric field, and we obtain these 3 eigenenergies. They correspond to some states. What's the eigenstate corresponding to these eigenvalues? क्या है eigenstates? नहीं हो सकती। जब इसके साथ corresponding eigenstate है 2 1 1, इसके साथ corresponding eigenstate है 2 1 -1, क्योंकि these I can write this lower block matrix, this block matrix. If I write this block matrix on its own, what are the elements of this matrix? The elements of this matrix are HP 2 1 1 2 1 1 2 1 1 HP 2 1 -1, right? So then these are the matrix elements. We have then 1 -1 HP 2 1 1 2 1 -1 HP 2 1 -1. ये मैट्रिक्स, ये जो मैंने ब्लू में लिखा है ब्लॉक मैट्रिक्स, दरअसल ये मैट्रिक्स है, ठीक है? और ये आइगन वैल्यूज इसकी 0 हैं क्योंकि it's 0. So what's happening here is that there is no correction to certain eigenvalues because these are actually shifts in the energies. But shifts in energy of which states? Of course, this block matrix corresponds to only these states. Okay, so the eigenvalues are 0. The eigenstates of this matrix will just be the states ket 2 1 1, and the other state will be ket 2 1 -1. Okay, and these are two of the original states. However, if we look at these eigenenergies, which means we consider this block matrix, this is not diagonal in the basis that we print. Therefore, therefore, the eigen states corresponding to these eigenvalues are not the original states, rather they are some superposition of the original states. And what are those states? These are just the eigenvectors of the polysigma X matrix. And what are those states? These are equal superpositions of. So what are the eigenstates of sigma X? This is sigma X. What are its eigenstates? The eigenvalues or the eigenvectors. So this is sigma X matrix. क्या होगी इसकी eigenstates? एक ये होगी, एक ये होगी, ठीक है? These are just the eigenvectors of the sigma X matrix. Consider the block sphere. Block sphere में x axis पे आपकी state line है, एक x axis लाई करेगी एक minus x पे. So what are the eigenstates corresponding to these eigenvalues? They are just superpositions of the original. So this eigenvalue corresponds to state 1 over under root 2, 2, 0, 0 plus 2, 1, 0. And this eigenstate, this eigenvalue corresponds to 1 over under root 2, 2, 0, 0 minus 2, 1, 0. Alright, so the states with the same mn value, they form the eigenstates in the presence of the perturbated Hamiltonian. We can also show what's happening diagrammatically. Initially, in the absence of an electric field, we had 4 states degenerate. Okay? All of them at the same energy. That energy was some minus E naught over 4, where E naught is 13.6 electron volts. Okay. Now, these states are 2, 0, 0, 2, 1, 0, 2, 1, 1, 2, 1, minus 1. All 4 of them have the same energy. Now, we switch on an electric field. Is non-zero. We switch it on. We see that nothing happens to the energies of these states. So these states continue having the same energy. Okay? 2, 1, 1. They remain degenerate. Okay? However, the degeneracy is limited for these states. Okay? And we get a state that is higher in energy and a state that is lower in energy from this datum value. How higher? It's E under 3 A naught and the magnitude of the electric field. This is also E under 3 A naught magnitude of the electric field. This axis is the energy axis. Now, which state is this? It's not 2, 0, 0, it's neither 2, 1, 0, it's actually a superposition of these states. Okay. So this would be 2, 0, 0. Now, this corresponds to the negative 2, 0, 0 minus 2, 1, 0, 1. And this corresponds to 2, 0, 0 plus 2, 1, 0, 1. So the degeneracy has been limited. The new eigenstates are no longer the eigenstates of the unperturbed Hamiltonian. These are the eigenstates of the unperturbed Hamiltonian. Unperturbed Hamiltonian H naught, we all know, is minus 1 over 4 pi epsilon naught E square over R. This is the potential energy plus, of course, minus H bar square M potential. Okay. Now, what we see is that the degeneracy is limited by the application of an external field. The eigenstates change, and we can also plot the variation of the eigenvalues, which are really the eigenenergies. So if I make a plot versus the applied electric field of the energies of the states. For two states the energies don't change. Okay? They remain where they are. Minus E naught. For one state the energy varies linearly with the electric field in the positive direction. And this state is this superposition. And for the other state the energy varies linearly but in the negative direction. So this is the DC Stark effect. You apply an electric field, you find that the energies change linearly with the applied electric field. Okay? Higher order corrections are also possible. We only consider the first order correction. Alright. Now let's look at another example. I am just doing more and more examples of perturbation. Let's do one more example. There's one example in your book of an infinite well and you apply a three-dimensional well and you apply a perturbation x, y. Yes? It starts at some energy minus E naught. Alright. Now let's look at another example. A very nice example, a comprehensive example. I'm taking up examples that are not present in your book so that you can get a wider perspective of what's going on. Now this example involves an ammonia molecule placed inside an external electric field. We know that there are two conformations of the ammonia molecule. The network of the hydrogen, the base of the pyramid, the three hydrogen atoms and a nitrogen atom. So it's a pyramidal molecule. There are two possibilities. Either the nitrogen atom would be above the plate or the nitrogen atom would be below the plate. And right? So these are two possible quantum states. And the degree of freedom we're talking about is the conformation of the molecule. So we call this state Ket 1 and we call this state Ket 2. Both of these states have the same energy. Okay. Let's call that energy E naught. Because there is really no difference between this energy and this energy. Okay. However, there is a possibility that if you start off in this state, Ket 1, you can tunnel into this state. Therefore, if you write the quantum mechanics one, we look at a more problem in which we would have a token. The diagonal elements are just the E naughts and they are the same. Okay, because the eigenvalues of this Hamiltonian will give us the energies. So if there were no tunneling possible, you would have 0 here and 0 here. But the possibility of tunneling means that Ket 1 is connected to Ket 2. There is a finite. You start off in Ket 1. With time you can go into Ket 2. Okay, so this matrix element tells us the transition probability. Okay. So we call that element minus A. Just some complex number. And if you start off in Ket 2, you can go into Ket 1 with the same amplitude, with the same probability. So there is a minus A. So this is your Hamiltonian in the absence of any applied electric field. Now suppose you do apply an electric field. And suppose that the electric field is applied along the z-axis. Okay, and the z-axis is the axis that connects the nitrogen atom to the base of the pyramid. Okay, it's a pyramidal one. So you can also introduce a perturbative Hamiltonian. So the energy of these states. Okay, let's first before applying the electric field, what are the eigen states? We have to find out the eigen states. Those eigenstates will turn out to be superposition of Ket 1 and Ket 2. ठीक है ना? कैसे पता चलेगा? आसान है। इन एक तो आप उसको सॉल्व कर सकते हैं। दूसरा भी कर सकते हैं कि H naught equals E naught into the identity operator minus A sigma x. So the eigenstates of H naught will be the eigenstates of sigma x. the eigenstates of sigma x are equal to propositions of the diagonal states. So you will get the eigenstates of H naught will turn out to be ket 1 plus ket 2 over under root and ket 1 minus under root minus ket 2. Okay. प्लस वाले की एनर्जी होगी, अब प्लस वाले की कुछ एनर्जी होगी, माइनस वाले की कुछ एनर्जी होगी. How will you find out the energies? You will have to diagonalize this matrix. Okay. So I can complete diagonalization energies corresponding to state 1 and state 2, zeroth order. Okay. This is unperturbed energies. I haven't applied the energies here. These are just given by the eigenvalues of this equation. So let's look at the eigenvalues. E naught minus lambda minus a E naught minus lambda, determinant is E naught minus lambda square minus a modulus square equals 0. This is E naught squared plus lambda squared minus 2 E naught lambda minus a mod square is 0. So this means that the energy eigenvalues E1, 2 up to 0th order are just the values of lambda here, which you get by solving this. They will be equal to 2 E naught plus minus 4 E naught square minus 4 E naught square plus 4a modulus square. So the energy eigenvalues are simply E naught plus minus a. Okay. So the eigenstates, the unperturbed eigenstates, psi 1 get up to 0th order is 1 over under root 2 ket 1 plus ket 2, and its energy will be E naught minus a. और जो दूसरी स्टेट है 1 over under root 2 ket 1 minus ket 2, इसकी एनर्जी होगी E naught plus a. This is psi. Okay. समझ गए? ठीक है, हम इसे मैट्रिक्स को डायगोनलाइज किए, उसकी अनपर्टर्ब्ड आइगन स्टेट्स निकाली, अनपर्टर्ब्ड आइगन एनर्जीज. इस स्टेट को मैं कभी-कभी कैट प्लस भी कह सकता हूँ, उस प्रोपोजिशन में इस स्टेट को मैं कैट माइनस भी कह दूंगा फॉर ईज ऑफ लेबलिंग. Okay. So we have found out the unperturbed eigenstates and the unperturbed eigen energies. Okay. Of course, these states are not degenerate. One has energy E naught minus a, other has E naught plus a. So if I draw an energy manifold diagram, one energy is E naught minus a modulus, the other is E naught plus a modulus, right? और इनके कितना सेपरेशन है? ठीक है? So Rabi oscillations can take place. Alright. Anyway, so these are the unperturbed states. Now I will apply electric field. So the Hamiltonian, as a result of the perturbation, will change, and the perturbated part of the Hamiltonian, ये क्या होगा? इस देखो, electric field interacts with electric dipoles. Okay. So this molecule has an electric dipole moment. Okay. That electric dipole moment is pointing from the plane of the hydrogens to the plane of the nitrogen atom, because the difference in electronegativity. So this molecule can be represented actually by a dipole moment, mu. It has a certain mu. It's the charge separation multiplied by the distance between the center of the nitrogen atom and the hydrogen plane. So it has a certain electric dipole moment. Now you place the electric dipole moment inside an external field, the energy will change. And we know that the energies are given by minus mu dotted with E. If the field is applied along the Z direction and its magnitude is E, then this Hamiltonian will become minus E Z operator, because this is what the electric dipole operator is. You can charge into separation E naught into applied field E, okay, and its magnitude. So this is our perturbative Hamiltonian. Mu की जगह मैंने माइनस C ली। ठीक है ना? अच्छा, मैं अगर इस देखो now there is some angle here between, this could be minus or plus. Why? If I apply the electric field, this term, if I apply the electric field, suppose the molecule is in the state cat 1, the applied electric field is parallel to the dipole moment, the energy will decrease. How much will the energy decrease? The decrease in energy will be equal to minus, the change in energy will be equal to minus E Z E. Or I can also write this as, okay, let's not spell out the EZ. Let's just write this as minus mu dotted with the electric field. Okay. Now I would like to write this perturbative Hamiltonian in a matrix form. Okay, and the basis I choose is the same basis that I have chosen here. Now if I have this conformation, the energy of the molecule goes down because the electric dipole operator is parallel to the field. If I have this configuration, the electric dipole moment is anti-parallel, so the energy goes up. So if I would like to write this operator in matrix form, what would I get? I would get a 0 here, okay. And here I would get a decrease in energy. And how much is the decrease in energy? Minus mu into dot product with the electric field. So I can just take the Z component of the electric dipole moment, because this molecule could be tilting in any direction, pointing in any direction. I can just take its Z component, which is parallel to the right, in E, which is the electric field. Okay, and here I will get plus mu G E. So my Hamiltonian is really, in the cat 1, cat 2 basis, is really minus mu Z E into the sigma Z operator. Okay, so this Z operator is really a shorthand of this E Z operator is really a shorthand of mu Z sigma Z. Anyway, this is the perturbative Hamiltonian. We apply an electric field, perturbation switch. We would like to find out how do these energies change with the application of an electric field. Okay. So could you find the first order correction to the energies? This energy, one of the energies is E plus is 0th order, this is simply E naught minus A. Okay. The second energy of other unperturbed state, which I will label by minus, is E naught plus A. Now I would like to find the shift in this energy and the shift in this energy. It's quite easy to do. The shift in this energy, E plus, up to first order, is just the inner product given by ket plus W plus HP. Now HP is something plus, right? This is the shift in the energy. ठीक है ना? अब अब bra plus I can write as 1 over under 2 ket 1 plus ket 2. This HP, which is this term, I can quite conveniently write in the following form. I can write everything in the ket 1 ket 2 basis. This would become, there's a minus mu z electric field, right? And then there's a sigma z operator. Sigma z is simply ket 1 bra 1 minus ket 2 bra 2. And this ket 1 is ket plus is 1 over 2 ket 1 plus ket, right? So after all of this, what do I get? I get half minus mu z electric field ket 1 bra 1 plus bra 2. This will become ket 1 minus ket 2. And this becomes 0. Up to first order, there is no change in the energy. Okay? Likewise, up to first order, there will be no change in the energy of the other items. Okay. Now notice one thing. If I write the total Hamiltonian H, which is the sum of H naught and the perturbation part, this is the result from the time independent, non-degenerate perturbation theory to the first order, only to the first order. If I write the total Hamiltonian is E naught, so minus A, E naught, plus the perturbated part is minus mu z E here. Remember, this is E naught energy, this is electric, plus mu z. What I would like to do is I would like to find the eigenenergies. Now this is exact, there is no approximation in this sample. I would like to find the eigenenergies in the presence of the electric. I can just diagonalize this matrix. Let's find the exact eigenenergies. Okay. So E naught minus mu z E minus lambda minus A E naught plus mu z E minus lambda squared plus 4a modulus squared plus 4 mu z squared e modulus squared divided by 2. So my energy eigenvalues, the exact values in the presence of any electric field whatsoever, because I'm not concerned about the strength of the electric field so far, they are just E naught plus minus a modulus squared plus mu z squared e modulus squared over a squared. Oh, sorry. A modulus squared. Right. So these are the exact ideal energies. The exact energies. Now, if my electric field is small, if I apply small electric field, small e, which means be a small mu z e as compared to modulus a. If I apply small electric field, these energy eigenvalues. Now this is exact, no approximation up to this point. Now I apply small electric field, which means the energy eigenvalues are E naught plus minus a 1 plus mu z squared e modulus squared over 2a squared and so on. I've just applied the binomial expansion. So this means I get these energies are E naught plus a plus mu z squared electric field squared over 2a, and the other energy is with a minus sign. Both of them minuses plus other terms. I already. So this is an exact result. This is an approximation when the applied electric field is small. Now from the first order perturbation theory, we see no change up to first order in the energy eigenvalues, and the energy eigenvalues truncate at this point. They are E naught plus minus a. So this term must be coming from the second order perturbation. So we can also find out the second order correction to the energy eigenvalues using perturbation theory. So what we have here is E plus the second order correction to this term. Okay, the second order correction to this term, if you use the perturbation theory, is given by HP is a ket plus a ket minus modulus squared divided by E plus unperturbed minus E minus unperturbed. This is the second order correction to the E plus term. This comes from the second order perturbation. Still non-degenerate. ठीक बात है. तो इसको देखते हैं कि if we reproduce the same result as we get from a binomial expansion of the exact result. So this is exact. This is just the binomial expansion of the exact result. There are higher order terms as well. This is from the second order perturbation. Up to first order perturbation, we do not get any connection. Let's see whether this term reproduces this term. That's what we're going to do. So HP plus minus, so we have to work this out. Okay, so let's work it out. HP, let's first calculate this matrix element. So this matrix element is, what is HP? HP is minus mu z E minus mu z electric field E. So 1 over 2 from this, 1 over 2 from this, get half. This becomes get 1 minus get 2. HP is sigma z, which is get 1 minus get 2. Okay. Here I get 1 plus get 2 minus mu z E over 2. And from here I get bra 1 1 plus 1, 2. So I get minus mu g e. इसका इनर प्रोडक्ट 1 है, इसका इनर प्रोडक्ट v1, ठीक है, get 2 है, 1 plus 1 minus 2. ठीक है. Now take the modulus square of this. I get mu g squared e modulus square. Now I have to look at the difference of these unperturbed eigenvariants, and this difference is simply 2a. So this exactly matches this result. So what we considered here is the weak field case. In the weak field case, the dependence on the applied electric field is quadratic in the weak field. Now this result is valid whether the electric field is weak or is strong. What do weak and strong mean? The relative magnitude of this term with this term. Okay, when I say weak or strong, it's appropriate to something. This expansion is valid only for the weak fields. Okay. And the time dependent perturbation, this time dependent perturbation theory is also valid for the weak fields. Now what we would like to do is see what happens when the applied field is strong, when this term dominates over this term. Now there are two different ways of approaching this. Let's figure it out. मैं आपको एक मिनट देता हूँ, अगर आप सोच रहे हैं। कौन सी? ये वाली? देखो ये तो मैंने इसको एक्सपैंड किया बाइनोमियल एक्सपेंशन, ठीक है, ये इसकी सिंप्लिफिकेशन है और कुछ नहीं। तो अब दिस इज एन एग्जैक्ट रिजल्ट। अगर हायर ऑर्डर का हमको सारी चीजें ये एग्जैक्ट रिजल्ट, ये टू परटर्बेशन थ्योरी। अब परटर्बेशन थ्योरी जब हम लगाते हैं तो फर्स्ट ऑर्डर में कोई जीरो करेक्शन आ रहा है, ठीक है। सेकंड ऑर्डर में जो करेक्शन आ रही है, जो हमने एक्सप्लिसिट फॉर्मूले से कैलकुलेट की, दिस हैपेंस टू बी दिस। तो our perturbation is exactly mapping to the binomial expansion, the exact result. Higher order perturbation भी करेंगे, इससे तो अगली टर्म हमको आ जाएगी। Okay. But we can apply this perturbation theory only when the applied field is weak. What do we do when the applied field is strong? There are two options. ठीक है, वो एक एग्जैक्ट रिजल्ट है। ओके, व्हाट हैपेंस व्हेन द फील्ड इज स्ट्रांग? आज हमने खत्म करके फिर एक स्पेशली एक घंटे का सवा घंटे का लेक्चर करके टाइम डिपेंडेंट मैग्नेटिज्म एग्जांपल। बट स्ट्रांग फील्ड में है, स्ट्रांग फील्ड में पहले एग्जैक्ट रिजल्ट देखते हैं। E1 2 we can expand the square root in the following fashion. We can have E naught plus minus, instead of taking a square as common, we can take mu z square e modulo square as common, right? 1 plus a square over mu sorry, यहाँ पे आएगा मैंने क्या किया, यहाँ पे म्यू सी ई आएगा ना इस तरह, है ना, और यहाँ पे म्यू सी स्क्वायर ई नॉट स्क्वायर, राइट, प्लस हायर ऑर्डर टर्म्स. So this means E naught plus minus mu c E plus minus a squared over 2 mu c E plus higher order terms. Now note that the energy eigenvalues have linear dependence. So this is the DC start. This is really a version of the start effect. Okay, in the strong field case, ammonia molecule placed in a strong electric field gives the same dependence as a DC start effect. Alright. Now this is an exact result. We would like to achieve the same result in perturbation theory. Okay. Now we know from perturbation theory the following fact. We have two eigenstates, ket 1, ket 2. Ket 1, ket 2 की ordering क्या है? Oh sorry, the eigenstates are ket plus and ket minus. This is ket plus, unperturbed, right? Ket minus. इसकी एनर्जी E naught minus A, इसकी एनर्जी E naught plus A. Now, if the applied electric field is large, what does this mean? This means that terms of this kind, H, P plus minus modulus squared E plus 0 minus E minus 0. So these terms appear in our expansion of the non-degenerate. Right? It's the second order energy correction and first order correction to the wave function. Now in the denominator we have a term, but in the numerator we have another term. This term will depend upon, we noticed that this term already depends upon mu c E. Right? So this term, which is in the numerator over there, is much larger than the denominator. In fact, this term is so small in the denominator that this can approach infinity. So the non-degenerate perturbation theory, the mechanism of formula will break down. In general, if we have unperturbed states and there is a difference in the unperturbed states, this difference here is 2A. Okay? And if your applied perturbation, the inner product of the applied perturbation, right, which is this inner product, is much larger than the difference between these states, then it's not advisable, it's not legitimate to treat these states as having different energy. They really have the same energy. Because this separation is much smaller than the term that is the term, because this is just a perturbative term that is connecting ket 1 to ket 2. It just gives me a frequency of oscillation between ket plus and ket minus. So if this frequency of oscillation is really large as compared to this energy difference, then this term can simply be ignored, which means that these two energies will come together. And we have to use the results of the degenerate perturbation. Okay? So now if the unperturbed energies, if we use the degenerate perturbation, then the unperturbed energies are just E naught, because this A is just 0. It's treated to be 0. Because this separation is so small as compared to the transition matrix element due to the applied perturbation that is connecting these eigenstates. So if HP plus minus modulus squared, if this term is much larger than the separation of energies, unperturbed energies, then we cannot use non-degenerate perturbation. We have to Okay, so how does degenerate perturbation work? Degenerate perturbation simply works by writing down the perturbative Hamiltonian in some bases and finding its eigenvalues, the eigenvalues. Now the perturbative Hamiltonian in some bases, which is our ket1, let's write this in the ket1, ket2 basis. We've already done that. It's minus E, capital E sigma z, which is 1, 0, 0, minus 1. Right? This is our perturbation Hamiltonian in the ket1, ket2 basis. What are its eigenenergies? The eigenenergies are simply minus E, capital E, into Z, minus E, sorry, mu Z, minus mu Z and plus mu Z. Okay, this is simply eigen energies यही होंगी और eigen states क्या होंगी? ये eigen state इसके साथ eigen state क्या होगी? ket1, ket plus ket1 और इसके साथ eigen states क्या होंगी? ket. So, alright, and this exactly matches the exact result. In the exact result, the unperturbed energy is E1, right, which is a zeroth order energy in the degenerate perturbation. Because in the degenerate perturbation, we assume that our initial states have the same energy. And what is that energy? It has to be E0. So it's E0, and the first order correction is minus capital E mu Z, this and plus mu Z E is this, right? And the energy eigenstates when the strong field is applied are ket1 and ket2. The energy eigenstates when a weak field is applied are not ket1 or ket2. They are something different. They are neither ket plus and ket minus. So you probably, I'll give this in the exam. What are the energy eigenstates for the weak field case? For the strong field case, the energy eigenstates are ket1 and ket2. Now this is something that you can figure out intuitively as well. Suppose I write the total Hamiltonian. The total Hamiltonian in the presence of any electric field H is simply given by E0 minus mu Z E modulus minus A E0 plus mu Z. Now, if this electric field that's applied is much larger as compared to these off-diagonal fields, then the eigenstate will simply be the eigenstate of the sigma Z operator, because the matrix will become that. However, if the off-diagonal terms are larger, if the off-diagonal terms are much larger than the applied electric field, that is, the electric field is really small, then the eigenstates will approach the ket plus and ket minus states, because then these terms will be approximately 0 as compared to the off-diagonal terms, and the off-diagonal term will make a sigma x matrix. So the eigenstates in the presence of a weak electric field will approach the ket plus and ket minus states. Somewhere in between, we'll have eigenstates that are mixtures of that is something like this. Some cosine theta ket1 plus sine theta ket. Okay? Where theta depends upon the relative magnitude, tan theta will depend upon the relative magnitude of A and mu Z E. So it will be, I think it will be mu Z E over mu A. Neutrinos के साथ में ऐसे examples mixing angles. So depending on the relative magnitude of mu Z E and 2A, we can get ket plus, ket minus as the eigenstates, or ket1 and ket2 as the eigenstates. So now what we've done here, we have done an exact calculation, expanded the eigenenergies, and found out that we got a linear dependence upon the electric field in the presence of a strong electric field. Then we used degenerate perturbation theory here, and we got the same result up to the lowest order. However, it's also possible to use the non-degenerate perturbation theory here. And how do we do that? We treat H naught. We can break up this Hamiltonian into any possible way we like. We can break this Hamiltonian as H naught equals E naught minus mu G E 0, 0, E naught plus mu G E. Right? We can call this H naught. Let's call this H naught. Now the eigenstates of this H naught will be ket1 and ket2, and the eigenvalues will be different, will be grossly different, because this mu G E term is large. So we can introduce a perturbating Hamiltonian, which is given by minus A minus A. Right? We can do that. Now the perturbation is much smaller than the unperturbed Hamiltonian. Now the eigenvalues or the unperturbed eigenvalues, the E1, 2 unperturbed, with this prescription, they are, what are the unperturbed? They are simply E naught minus mu G E and E naught plus mu G E. Okay, so these are just these terms. Now what we would like to do, we would like to find the first order correction to these energies. Okay, can you immediately tell me what the first order corrections are? So the eigenstates are of course ket1 and ket2, right? These are the unperturbed eigenstates. Now the first order corrections will be given by HP ket1, right? This is the first order correction to E naught minus mu G. What's this term equal to? इसी तरह के HP ket is also. So the first order correction to the energies which we have found here is 0. Let's now apply the perturbation theory to the next order and see if we can reproduce this term. देखो आपने degenerate perturbation theory भी इस्तेमाल कर सकते हो और non degenerate perturbation theory भी इस्तेमाल कर सकते हैं to break up your Hamiltonian property. If you break up the Hamiltonian property, it means that these energies are widely different as compared to the perturbation. So you can use non-degenerate perturbation theory. But in this case, you have to use degenerate perturbation theory because your perturbation is much larger than the energy separation of unperturbed states. They're too close together. Okay. So now up to second order, let's calculate the second order shifts to the energy. E1, let's do it first order. E1, right? Second order is ket1, HP, ket2, right? We take the other state, modulus squared E1, 0th order, minus E2, 0th order. Okay, now what is this term equal to? It's just a modulus squared. ठीक है? Divide करेंगे E1 minus E2 से. Get minus mu G. And this exactly matches what we have here, right? The minus 1. Okay, so So now we can apply degenerate, non-degenerate perturbation. We have plenty of examples of time independent perturbation के पिछले लेक्चर पिछले हफ्ते भी की, इस हफ्ते भी की, काफी सारे एग्जांपल्स हमने देख लिए। अब अगले क्या आप अली ठीक है क्या आप लोग कल फारिग में 2 से